I wanted to get started here. Welcome to Earn Your Simulation Degree in 90 minutes, hopefully less. If you guys have any questions, feel free to ask, but make sure that the questions you ask I actually know the answer to, because I'm trying to look good. So make sure we do that. So I didn't know how to start this presentation, so just wanted to start with a joke. Anybody know the answer to this question? Enough to break the ice. There you go. All right, so this is called Earn Your Simulation Degree. And the way I look at it, it's the knowledge that you need, the foundation that you need to be successful with using SolidWorks simulation. So I sort of broke this down into different courses, going with this academic theme. We're going to get started with a really high-level introductory to SolidWorks simulation, what it means from a business aspect. And we're going to call that course Business 400 SolidWorks Simulation Synergistic Integration. Yep. And then we'll move on to Simulation 101. That's going to be the very fundamental basics of finite element analysis. Then we'll move on to Engineering 201, which is pretty much just all the essential information that you guys might need for material science. So we're going to call that Material Science Essentials for Professionals. And then we'll go into actually the mathematics behind the scenes of finite element analysis. So numerical methods for better designs. And finally, we'll go into SolidWorks simulation. Specifically, we'll actually play around with the software and talk a little bit about the specifics of the tool. So first things first, a little bit about me. My name is Steven Petrock. I grew up in the Northeast in Pennsylvania. I went to school, studied international affairs and mechanical engineering. I've lived in Germany, Washington, D.C., where I was a tour guide. I also worked on the railgun at the Naval Research Lab. And then I moved to Orlando to work for Modern Tech, another reseller for SolidWorks, where I'm the simulation specialist, also the director of our technical marketing, also the head of our online training. And this is my second year presenting simulation at SOLIDWORKS World. So I think I want to start first saying what this isn't, what you guys aren't going to get out of this. This isn't a sim tutorial. We're not going to go into the picks and clicks of the software of how to use it. I can certainly help you out with that. I can point you in the directions of some great tutorials. I can sit down with you and show you how to run the software. But really I want to make sure you guys understand the fundamental concepts of finite element analysis and the theory behind it. So we're not going to talk about advanced topics, tips and tricks, and it's not going to be advanced simulation techniques like how to deal with meshing, mixed meshing, mesh diagnostics, all this nonsense that we're not going to deal with today. But we can if you want to. So let's get started. Simulation, synergistic integration. So what is simulation? Why is it important? Well, to me, simulation is GPS for CAD. It's this tool that we use to navigate through the design process, helping us decide what we're going to do throughout our design. How thick do we make this rib? How many cutouts do we need? How light can I make it? So granted, the earlier explorers used things like sextants that I have there. I hear you guys used to use maps to navigate. Nowadays, it's best-in-class technology, GPS, your iPhone, getting you from A to B still, but you're getting there much more efficiently and much more effectively. So what I look at simulation, I think of it as this application of some of the greatest works of art of all time. So I want to tell you guys a little personal story here. If you were to ask me what I thought about art, I would have told you in elementary school, middle school, and high school that I hated it. So I hated art. But I don't think that's a fair question, because all I ever did in art class was draw a little, I would trace my hand and draw a little turkey, or I would draw a tree. So the question really is, I hated drawing trees and drawing turkeys. But even though that's all I ever did, I still knew all these works of art, all these great works of literature. So how comes people get taught mathematics and science and they don't have an appreciation for the beauty behind the scenes? So that's kind of what I'm here to do for you guys today. So I want to try to help you learn the fundamentals so you have a confidence level to use this tool, but also hopefully to inspire you guys to want to use this and have this appreciation for SolidWorks simulation. And also just a quick question. Anyone know what that Latin is on the bottom? Anybody? So the first one is actually, it's the original anagram that was published by Robert Hooke. That's actually Hooke's law, and that's how it was published when he originally published it. But we'll get into that later. So what really is SolidWorks simulation? It's a mathematical method for solving very complicated problems. So it's just this application of this theory that was done in the 1400s, 1500s, and 1600s by people like Robert Hooke, Galileo, Newton, and obviously on the left-hand side there, that's Newton, but he's in a square meter, so we put Pascal in there. Yes, so some guys got that joke. So the reason we use simulation is to get answers to questions like, is my part strong enough? Is my design durable enough? Will my part overheat? Is it going to be safe? Will it maybe vibrate and fall apart? Is it going to collapse under things like buckling? So we have all these different study types in SOLIDWORKS Simulation that we can do to help get these answers to these questions so that we can have better designs, get them out to market faster. Also, we can have this confidence level where we know no one's going to get hurt from our designs. They're safe, they're durable, they'll last, so you can sleep well at night. So I'm going to give you guys an abridged version of the complete history of SOLIDWORKS CAE. We all know 1995 SOLIDWORKS came out with the first release, the first CAD package built on the Windows platform. It took 1 year to be recognized by the company SRAC, who had this software called Cosmos. They repackaged it, and Cosmos actually was the very first gold partner to SOLIDWORKS, and it took 1 year for that to happen. 5 years later, in 2001, SOLIDWORKS purchased that company, and 2 years later, 2003, we released Cosmos Express. And then there's some more tools that came out. Cosmos became simulation, flow simulation was introduced, plastics was introduced, and here we are, 2014, at SOLIDWORKS World. So I want to point to 2003. That year was very important because what happened was we had analysis on the desktop of every single designer. Every single seat of SOLIDWORKS came with Cosmos Express. So in 1995, the thought was if you can use Windows, you can use SOLIDWORKS. Well, if you can use SOLIDWORKS, you follow the same intuitive workflows you can use simulation. So if you look at those 2 points, what we're really saying is if you can use the Windows operating system, you can use simulation. So everyone agree? Anyone disagree? All right. So I get this a lot when I'm talking to other people who are full-time analysts that love using these. They like to feel like they're at the hands of that they have like a space shuttle, they're in control of something that looks complicated. But SOLIDWORKS takes a different approach to it, right? We want to make a tool that's intuitive, that's easy, it's elegant, but it's also powerful. So we can't confuse ease of use with simplicity or lack of functionality. So just because we take everything and hide it from the users and disguise it with this very elegant and beautiful user interface doesn't mean the power driving it is not the same. Because it is. As I said, it's just those equations from the 1400s, 1500s, and 1600s, really. So that was my business. That's business 400. That's advanced business for us. So let's get into the fun stuff. So finite element analysis for freshmen. Let's talk a little bit about what FEA really is. So here's my little flow chart for finite element analysis, what this is. You start off with your CAD model. Now, if I have something like a chair or this table or a bracket, I can't just ask the question, is this strong enough? Okay? I can't get that answer right away because it's too complicated of a problem. We have to break it up into many simple problems so that we can solve it, right? We deal with complicated shapes, large assemblies. We can't solve everything all at once. We have to break it up into smaller, simpler problems. Then we press run. The software solves all these equations for us, and it gets all these simple answers to these simple problems, and it stitches them all back together, and that's what we see as results, like factor of safety or any other plots that we get in simulation. So when we're dealing with this, that was just more a generic workflow. Here in SolidWorks specifically, this is what it starts with. It starts with your CAD model. You have this SolidWorks CAD model, and here I have the screwdriver, basically just one solid geometry. I look at it as one impossible problem. We go into simulation, we set up the problem, we apply the loading to it, apply the fixtures to it, break it up into many simple problems, and then all we do is we press the run button, and then simulation takes care of the rest and presents us with our results, solving all those simple problems and stitching everything together for us. And that's what we see in our one final solution. So the way I look at this is there's two teams, two players playing on Team FEA. There's us, and then there's SolidWorks, or what I call the computer. We're responsible for the CAD model. We're responsible for setting up the problem, and we're responsible for looking at our plots. Computer's doing all the heavy lifting. It's doing all the hard work for us behind the scenes. It's solving these hundreds of thousands of equations for us. So if you look at it, your computer, SolidWorks, and you are actually a team playing on Team FEA. So FEA Solvers Solve FEA. Just like a calculator calculates and a computer does what? computes. So in the FEA world, there's, it's a mathematical application of certain equations to solve problems. All these softwares are different really just because their user interfaces are different. The command languages might be different. Even the language of the interface might be different. One person might be using Japanese, one person might be using English. So everything's the same, but what's hidden from you is the math and the science behind the scenes. So if someone said solve 2 plus 2, would you pick the space shuttle or would you pick your iPhone calculator you know how to use? Who wants to use the space shuttle? You're not, he's not. That's a good idea. I haven't used that thing in a while. He said you could use your brain. So, behind the scenes of FEA, we have this one very simple equation, F equals KD. Now, in these 3 letters, all you have is really just accumulation of all that you guys know about physics, engineering mechanics, matrix algebra, and differential equations. So looking at those 4 bullet points or 4 boxes there, how many people just got a little, just kind of cringed a little bit and said, I don't, anybody? I do. So what I say to people who get intimidated by looking at an equation like this is really just because you're not looking at it in the right light. Something that looks like this, that's just nothing more than a pile of garbage, really, can look pretty good if you just look at it in a different light, and that's what we're going to try to do here. So just one example of that is some of this artwork here. It's just a pile of garbage, but with just a different light on it, it actually looks beautiful, and So that's what we're going to try to do. So with this equation, F equals KD, you have 4 things that make up this pot. You have your loadings, material properties, your constraints, and from that you get your results. So this is just one example of it. We have this piece here, and I put a fixture on the one side. Basically, I'm clamping it or I'm holding it. I have this certain strength or stiffness defined by the material properties, and then I apply a loading. And that's my responsibility. That's what I'm going to do. I set up the problem, and then I press run, and then SolidWorks does the solving of the equations for me. And as we pull it, it'll expand. So does that work as everyone thought it was going to? Yeah. Okay. Good. So there's really 3 ingredients to this equation. You have 3 inputs. You have your loadings, your materials, your constraints, and all these things add up to your results or your output. So you put something in, you get something out. If you type in 2 plus 2 and you got 7, it's not really a problem with the software. You didn't type in 2 plus 2. It's kind of the way. I don't actually say that, but I'm thinking it. So the F equals KD, that's the 3 things, but there's 4 boxes. 3 inputs, 1 output. You have the F, which is your loadings. Your K is defined by the materials. And then you also have this thing here, D. It's actually being solved for as a result, but it also could be an input as well. So F goes up there to the left, the K is the materials, and then the D is for the constraints and the results. And we'll talk a little bit more about that in a little bit. But that's very important there, that the D, or the displacements, really is your result. So let's talk a little bit more about that K, or the material properties. And specifically, I want to talk a little bit about stress. That was one of those results that I had listed there. So when I asked you guys, stress, what's the first thing that comes to mind? Hopefully, you guys are all engineers, so it's probably not something like this, right? Is it? Okay. And that's fine, because there actually is a curve that defines how well we perform as human beings based on the stress that is applied to us. Now, people might be under different kinds of stress, but it affects your performance. So we can map exactly how well we'll perform socially or professionally based on the amount of stress that we have. Same thing goes for materials. All right? So in FEA, we have stress not as our performance of, professionally or socially, but it's the description of the intensity of a force on an object. So with that definition there, if you look at our 2 weightlifters here, who's using more energy, who's using more effort, who's using more strain, and who's under more stress? They're all related, and we all agree that it's the one on the right, right? No one? You guys awake? How was the morning session? Was it good? You guys like it? Who went to the ballpark last night, the CSWE event? That was fun, right? He was there. I was there. It was fun. It was the best one yet. So those 4 things there, energy, effort, strain, and stress, those are actually all related, and we'll talk about that a little bit later. So what I showed you there was that stress versus performance curve for human beings. The performance of a material is what we call the strain. So we have stress versus strain, defining the roadmap or defining the performance of this material. So why strain? Well, it's because it's something that we can easily measure, because the strain is really just the amount of deformation. We can take a ruler or a set of calipers or a yardstick, depending on how much stress there is, and actually measure the deformation of it. So if you increase the loading, you're going to increase the deformation. By increasing the loading, you're going to get more stress and more strain. Even though they're 2 separate columns, they're all related. And they're all solved for by something we can easily measure, and that is the displacement. So every single material has a different performance curve, or what I call the roadmap of simulation. So you have your steels, your aluminums, even us human beings, bone, our muscles and our tendons, every single thing has this curve that relates the intensity of a force on us to our performance. Now we might describe performance differently, right? How well we work, how much it deforms, or how much that grizzly bear can lift, but it's all the same. So let's take a look at a generic stress strain curve. And we can divide this up into 4 different regions with an extra point there in the middle. Now the first region all the way on the left is given the name linear elastic. All that means is as we stress an object or apply force to it, its displacement is going to be related to that stress linearly. It's going to follow a straight line. And if you remove the stress or you take the loading off of it, if I bend something, it's going to be stressed. If I remove the loading, it's going to go back to its original shape. Now once I get past that linear region, you can see the curve start to arc up to the right. And that's what we call the plastic region. So what that means is no longer is stress and strain linearly related. Now the changes are permanent. Once you remove that loading, it's going to go back to 0 stress, but its shape is going to be different. These deformations are now permanent. And then we have this point M. This is the maximum stress that an object can sustain. So after this, after you hit this point, all of a sudden now the stress will start to decrease, necking will occur, and ultimately it will fracture. We're not going to talk about necking or fracture, and also we're not even going to talk about ultimate strength either here, because us as designers need to concentrate only on this linear region when we're doing SolidWorks simulation. So how does this relate to the stress strain curve? How does it relate to our models? Here I have that exact same thing that I showed you earlier. All right, and we're pulling that, and you can see, if you guys look at the graph, we actually have that point right there following this linear line. As I pull it, I'm deforming it. There's going to be a certain stress. I can measure the deformation, and I can relate that to strain, and I can relate that to stress. And it's all following this roadmap here. Okay? You guys want to see that awesome animation again? Was that a yes? Oh, okay. So I pull it, I can measure it. What I'm measuring is the strain. Because I know where it's going to be on the y-axis, I can figure out how much stress is in there, and we can design to that stress. There you go. Look at that. All right. So I showed you that graph that had certain regions on it, and I also mentioned that we're only going to concentrate on that straight portion of it, that linear elastic region. Because that's what we're going to do with SolidWorks simulation. We define that line, or the slope of that line, via some material properties inside of SolidWorks simulation. So why is that important? Well, because that's what we call the elastic region, where I stretch something, it's going to go back to its original shape. It's always going to stay on that straight line. But if I pull something too much or stress it too much, all of a sudden now I reach this threshold or this level where the stress is too intense for it, and it's going to do something else. Now, when I say do something else, the way I look at this is, all right, I'm always going to follow that curve, straight line up, straight line down, straight line up, straight line down, until it's too much stress. It's like when I drive to work, right? I take Interstate 95, which I've hated all my life. I've lived on it, Pennsylvania, and DC, Miami. It's terrible. Anyway, I always take that road to work unless there's too much traffic. If the traffic's too intense, I'm going to find a different way home. And that's what these materials do. If you look here, it follows the straight line up, but then all of a sudden it reaches that intensity point, or what we call the proportional limit, or yield strength, whatever you want to actually call it. After we get past that point, now all of a sudden we're still going to go home, but we're going to take a different route home. And what it does is it follows a straight line back down. But if you look, we're at point B now, right? The path it took was from A to B to go back down to the bottom after we took the loading off it. It didn't make it home to its initial point, right? It landed at B, so it's a different place. The intensity was so severe it changed the way the model behaved. And that's not what we want to do as designers. We want to always be able to describe and predict what's going to happen with our model. So we're always going to want to stay on that linear portion. Now, if you guys do want to do more advanced simulations and actually model that, we can do that, but that's in our SolidWorks Simulation Nonlinear package. So when we talk about the strength of our materials, right? When we stress something, how much does it strain? Or when we stress something, how much does it bend or deform? We're defining that as the strength, or its ability to resist deformations. So that's, us, that's what we see, but we don't actually see what's really going on behind the scenes. So this is all related to the microscopic level. The strength of these materials, whether it's aluminum, whether it's steel, it's all defined by the atoms actually, and how they're actually connected to one another based on their interatomic bonds. So chemists go in there and measure the actual force it takes to stretch the atoms, and we see that at a macroscopic level as the part actually bending. So there's an attraction between these atoms and all this other stuff. Basically, the deformation or the force is the energy that it takes to separate the atoms, and that's what we see. So really quickly here, I wanted to show something. We have this bronze sample here. On the left-hand side is a real-life image of it. On the right-hand side is a snapshot of the SolidWorks material database. And what I want to look at here is we see things at the macroscopic level, and it makes sense to us, but not many people actually get a chance to see what this looks like at the atomic level or the atoms level. So I recorded this off of PBS. We're on so it's that sample of bronze, and we're just going to keep zooming in and zooming in and zooming in and zooming in and zooming in. And gets you see the grain structure, you see all the different groups of the atoms. And there as we keep moving in, we had to switch microscopes because now we have to get to an electron microscope. Anyway, we keep zooming in a little bit more. And ultimately what you guys are looking at now is the actual atoms themselves. So by us bending something or stretching something, that first image that I showed you, us pulling that, is really just nothing more than us separating the atoms. So does that make sense? How many people have seen something like that before? Cool. It's actually on Netflix. It's called Hunting the Elements. It's a Nova show on Netflix. Totally recommend it. 90 minutes of just elements. All right, so if you're taking me out on a date, I would want to watch that show. So what are the essentials? What are the takeaways? What really do you need to know about your materials, about your atoms, to define this in SolidWorks Simulation? Well, this is a snapshot of the material interface inside a SolidWorks simulation. Now, it looks a little bit different than the SolidWorks one, even though it's the same materials. Now, if you guys notice, some of them are in red and some of them are in blue. You guys see that? All right, so red is telling you you need these things. You absolutely are required to know these 4 material properties. And you might need to know the things in blue depending on how it's loaded or depending on what kind of study you're doing. So you have the elastic modulus, your Poisson's ratio, mass density, and the yield strength. So those are the things that you absolutely need. So I'm going to talk a little bit about that. The elastic modulus, that defines that slope of the line, right? We're saying we're going up this straight line on that stress strain curve. This elastic modulus or Young's modulus or the modulus of elasticity, that defines how stress and strain are related for a particular material. You need to know that. And then there's the Poisson's ratio, which defines Poisson's effect. So you have this group of material, right? You're not adding to it, you're just kind of changing the shape, moving it around. It defines how these changes in shape are going to occur. So if I pull on something, it's going to stretch but it's also going to get skinnier in the other direction. So you can't ever change the volume of it because you're not adding to it or taking away atoms. You're just kind of moving them around. So the mass and volume is always going to be the same. And then your yield strength, you need to know that because, well, that's the limit. That's our threshold that we're going to design to for our SOLIDWORKS designs. Because after that, our changes are now permanent. So this is what we're going to design to. Anybody have any questions so far? No? Okay. Oh, does everybody have a QR code reader on their phone? You might want to, you'll be able to download this PowerPoint at the end if you have a QR code reader on your phone, just so you know. So just think about downloading it. So let's move on to applied math, numerical methods for better designs, the actual mathematics behind how we look at our materials and get our results. So this is that same picture I showed you earlier. Now we're going to deal with the simulation setup because that really is defining our mathematical model that we're going to use. So let's talk about some finite element analogies. If I want to go in and measure the deformations, right, that's what this equation is doing. All I'm doing is measuring it. I'm measuring D. I want to know how much it's displaced, how much it's strained, what the stress is. Taking these measurements, something like this. If I wanted to see how far Mr. Mailman has to go from my house to the post office or to the mailbox, I can lay rulers end to end. Now the accuracy of my measurement depends on the size of my measurements I take. Same thing here. If I want to measure the area of this weird shape, it's kind of hard to do. So I'm going to measure it with things that I can easily measure, like these squares. So I can get that answer, or if I make my squares a little bit smaller, you can see how I'm getting more and more accurate. The same thing here. If I want to measure this circumference of this circle, well, I can measure it in straight lines, and it all depends how small my measurements are. So what we're actually measuring is the displacement, and the way we're doing that is by a spring model. So we have this block, this solid inside of SOLIDWORKS here, and we break it up into springs. So we see our fixtures, we see the actual springs connecting it. Now, the measurements that I take, or the size of my measurements, is defined by the size of my springs. So, how many springs? How many measurements? Which is how many problems I'm going to actually be solving. And if you guys know finite element analysis, this is how many elements. So, as you increase your number of problems, or the size of your measurements, all you're really doing is costing you a lot more. But at the same time, your answer might start to agree more closely with the real world solution. You're increasing your accuracy. So as you increase the number of problems or the measurements, you increase your time, your hardware resources, ultimately your money. But you get accuracy. So here we have this battle that we have to fight. So what are we going to look for? Well, there's this thing called the simulation sweet spot. So how many problems? What's the size of my measurements? That's the question that I get asked a lot. And I always say you want to make sure your answer is converged but convenient. Converged meaning you're getting an accurate answer, but convenient means it's within your resources. It doesn't take a month to run. It doesn't cost you $15,000 to get a supercomputer. It's not costing you a lot of money. It needs to be converged, which is accurate, and convenient, which is within your resources. So let's talk a little bit about that. What does convergence look like? Well, as I start to break up my geometry into these small shapes that I can easily measure, or these elements, you can see here I took, starting from the left to the right, I took 10 millimeter measurements, and then 5 millimeter measurements, and then 5 in some places, in some places 2 millimeters, and then 3 millimeters, and then in some places 1, and so on. And as I keep doing that, you can see my stress, or the accuracy of my level, start to increase until a level of about 80, where now all of a sudden the change between the 4th one and the 5th one was actually 0. So what did I do? Well, by taking more measurements, all I did was cost myself more money. I just kind of wasted a lot of time. But I did get to watch more Netflix while my boss was paying me, so that was good too. So that's a personal decision. So when we talk about conveniently accurate, right, we're talking about the time that it takes to solve, or the resources that are required to solve this. So as you break this down, we're going to call this a coarse breakdown, a moderate breakdown, and then a fine breakdown. I tried really hard to not use the words like mesh or size and all these things, so I did that on purpose, just so you know. So we're breaking this down into 1,700 points, 7,000 points, and then 16,000 points. And from the baseline, that was an increase of 300% and then 800% on the size of our problem. So how did that affect our results? Well, the time it took was up 150%, but the change in the stress was only 7.8%. And then the time went up 400%, and the change in stress from the baseline was 6.9%. So what that's telling me is, I think I had my answer beforehand with the moderate breakdown. By increasing it 400% really just cost me more money. So that's what I'm talking about with a converged solution or an accurate solution, but it has to be convenient. So why do we use simulation, and why are we doing this to solve these problems? Well, here's a really basic one. See, I broke it up into two elements or two springs, and this is the mathematics behind it. It's F equals KD. K is the material property or the strength. F is our force or our boundary conditions, and we measure the displacement. And we build this matrix, and it's a problem that we can solve. Now this is a very, very simple 1D problem, and there's 3 nodes in there. Imagine problems, like most problems, are about 100,000. Who would want to solve 100,000 by 100,000 matrix? Anybody? That sounds like a fun Saturday. So, what was that? All right, so when I talk about these simple problems, how we're breaking it up into these springs. Well, there's different types of measurements that we're going to take, or different types of elements that we're going to use for different types of situations. Now, this is unique to SolidWorks simulation here. We have our 3D triangles or solids, 2D triangles, which we call shells, and then we have 1D lines called beams. So we're going to deal with solid shell and beam elements in this presentation. There's other types of elements that we have in SolidWorks simulation. There's other types of elements that we actually have that we kind of hide from you, that we don't let you know that we have, but we have around 12 different element types. So why are we talking about this? Because, well, different elements are appropriate for different situations, whether it's solid, whether it's thin, whether it's a beam. Even though it's the same mathematics, the same type of problem, it's just an appropriate representation of your geometry. So let's take carbon, for instance. When I propose to my girlfriend, if I gave her a hunk of graphite, she's going to be really mad at me, even though it's the same carbon atoms. She wants the diamond. Okay, fine. That's the appropriate hunk of carbon to give to her. It's kind of... I'm actually probably going to try that. Anybody try that? Would you recommend doing that or not? Would that work for you? She said it would work. I'm not that strong. So let's talk a little bit more about these element types, these solid, these shells, and these beams, and then a specific type of beam. There's a solid element that is a tetrahedron, shell element, which is a 2D triangle, beam, which is the line, and a truss, which is just a special type of line that doesn't only resist axial loads. Something like maybe a wire rope would be a good example of that. Now, for each tetrahedral shape or solid, there's 2 types. There's linear solid elements or parabolic solid elements, or linear as in draft quality and parabolic as in high quality. And all we're changing there is the number of nodes. And the number of nodes, that's actually where we take our measurements. Now I said we can measure something very easily. We can measure the displacement. Well, that's where we take our measurements. It's at those points, those things we call nodes. And because it has 3 degrees of freedom, that's what we say, that means we're basically just taking 3 measurements at that one point. So a shell element has 6 degrees of freedom. So it has the same 3 that the solid has, displacement in x, y, and z. Since we're 3D space, no one's using AutoCAD anymore. So then we have shell elements with 6 degrees of freedom that has those 3 displacements in x, y, z, but also 3 rotations about x, y, and z. And then you have your 2D beam elements. Now, I like those a lot because anybody use weldments? Oh, hey. All right. So when you're using simulation, if you have a surface or if you have a sheet metal model, it automatically gets meshed for us via a shell. If we have any sort of weldment, it's going to be automatically meshed by SolidWorks simulation with a beam, because that's an appropriate representation of our model and does it for us automatically. And some of the more common element types that we have are what we call planar elements from 2D simplification, plane strain, plane stress, and axisymmetric, but that's for earn your master's in simulation, not earn your degree. So let's talk a little bit about mesh quality. The difference between the parabolic elements and the linear elements, or draft quality versus high quality. So what that really is just a checkbox in the mesh quality dialog box. So why is this really important? Well, what was that? Something like that, yes. We're talking about accuracy and convenience for us. So this is what's really going on behind the scenes. That very first equation I showed you, F equals KD, all we can measure is the D, the displacement. So this is what's going on behind the scenes. It calculates the displacement, takes the measurement. From that, because we know how stress and strain are related, we can calculate the strain from the displacement because of Poisson's ratio. And then we can calculate our stress from the strain. Now what's interesting about that is step 2. That's where this makes the huge difference. So it's not just that it's adding more nodes or taking more measurements. The problem really is that there's a calculus operation going on behind the scenes. By having a linear edge, we're taking a linear measurement. Well, strain is related to displacement via a derivative. So if we take a derivative of a linear edge, we're going to get a constant. But if we have a parabolic edge, if we take a derivative, now we have a linear description of that displacement. But what that also means is now, throughout that triangle, we no longer have just constant stress or strain. We have a linear description of stress and strain. So yes, it's going to take more time because there's more nodes, but it's also going to affect your accuracy. So that's a very important thing to know, that that's what you're doing. So there's a difference there between draft and high quality in not just the number of nodes, but the accuracy as well. So this is just what it looks like, and we're going to hop into SOLIDWORKS here in a second, and I'll show you guys a little bit about this. So we have 4 nodes at each corner there on the draft quality with linear geometry giving us an answer that is a constant. When we have high quality, we have parabolic edges because we add an extra node. Well, there's 6 edges, so now we have 10 nodes. It's parabolic geometry, but now it's a linear answer throughout that solid. Now, if you look at the nodes 4 versus 10, at each node we're taking 3 measurements, so it's 12 versus 30, so you can see how it's more accurate, but it is going to add up in time. So let me switch over here. So what's the difference between these elements? What does this really look like? So if I come in here and I draw, so real quick, I just drew one line, and if I want to get back into that exact same command, you guys know this shortcut, if you just hit the enter key, it goes back to the last command you just did. Who knew that? Who did not know that? Who just learned that? Right, so I'm going to do line, and I'm just going to draw it. I want to go back to the line command, draw it again, hit enter, and then I'm back in. So this is my element. This is actually a shell element. It's just a triangle. It has 3 nodes. Those are the endpoints of each of the lines. But when I pull on this and apply force to it, notice that these lines are all moving here linearly. If I add those, the difference between high quality and draft quality is just what we call a mid-side node, a node that gets added right to the center of each of the edges. So by doing this, I can actually come in here and pull on it and displace it. Now, that displacement is not a straight line, but it can map to the exact geometry via a parabola, which is a much more accurate capture of how this thing's really deforming. So does that make sense to us? I mean, that is called Jacobian. We don't want to deal with that. So does that make sense to you? All right, so here we have a grouping of 4 triangles. And you can see that they're sharing nodes. Every single element, or these triangles, is joined at these points. So here I have a node, another node, here, here, and here. Each one of them is a unique element. So I have green, red, blue, yellow. So this is a shell element that I have here drawn. It's basically just this flat surface. It has a thickness defined behind the scenes, but we're mapping to this geometry with a surface or a planar element. Shell element, sorry. So what's the difference between a shell and a solid? It's basically just same sort of shape, a triangle, that gets folded up at a certain angle. So it's basically just 4 triangles put together, folded up to make a solid triangle. And it looks like a pyramid, but a pyramid has a square bottom. So, who has seen a tetrahedron before? I have a shirt that says I love tets. I don't know where to go get a chunk of carbon. They don't sell that at the store, do they? So let's move on here to the last step, SolidWorks simulation. After all of that stuff, all the slides that I just showed you, it's really just the theory behind the scenes, what's going on behind the scenes. To go through SolidWorks simulation, you really have to know that it's a 5-step process, and you start at the top and you work your way down on the bottom. So where you see parts, that's where you define your material. Connections, right? That's how you define how these components interact to one another, if they're multi-body parts or if it's an assembly. And then you move down to step 3, that's applying or defining your fixtures. Next is your loads, and finally you define your mesh. So it's a 5-step process. If you forget the order, it's fine. It's right there for you, just top to bottom. We can all handle that, right? Yes? Cool. Sure. So let's do one example of a problem here in SolidWorks simulation. So I have here a landing gear, and I'm sure a lot of us kind of came here and flew here, and I really hope that it was designed well. I hope it doesn't break, but we'll test it, it's okay? So this is my model. It's an assembly made up of several parts. To get started with a simulation study, I have to click on the simulation ribbon up top in the command manager. Now I click my drop down there, and I can choose what type of study I want to do. So I want to do a static study. I want to figure out how strong this is. I want to make sure it's safe enough and it's not going to break. I can do all sorts of other different studies if I want to understand if it might buckle or if it's going to react nonlinearly, or if I want to go towards optimization, I can do that. If it's going to fatigue, I can do that as well. Or here I can have this option to get access to other element types like those planar elements, those other 3 types I mentioned as well. So let's just do a basic strength test here. So where do I start? There we go. Step 1. Apply material to all. So here's my database. Remember red versus blue, right? This is different than what we see in SolidWorks CAD. Now, if we apply materials in SolidWorks CAD, it'll automatically go to simulation, but what we do here won't automatically go backwards into our SolidWorks CAD, so you don't need to worry about that. So here, you can choose the material model that you're going to use. Remember I said we're going to stay on that line, that linear elastic region? So that's the model type we're going to choose. If we had chosen a nonlinear study, if I were to click this box, here I only have 2 options, just 2 different variations of linear elastic. One is isotropic, one is orthotropic, or some people might call that anisotropic. It's basically just like wood. You pull on it one way, it's fine. If you go with the grain or against the grain, it's stronger or weaker in different directions. If I were doing a nonlinear study, I would have a dozen or so different material types, material models I can choose, whether it's hyperelastic or something like nitinol, shape memory alloys, all these different material models I can choose. So here I'm going to do linear elastic. I can choose alloy steel or any of the other materials. I can define my own. Or if you're on 2014, you can go to the materiality web portal. Has anyone seen that? Anyone not seen that or heard of it yet? It's called materiality. What that is, it's this new button that we added to SolidWorks Simulation, where if you click on it, you have access to thousands and thousands and thousands of different materials, even fully defined stress strain curves for tons of different rubbers and plastics, even metals as well. So you go in there, it brings you to a web portal. It's the exact same interface. You say, I'm doing a static study with this model, or I'm doing a nonlinear study with this model. And you can start filter through all these different materials. And it's published by a company called Materiality that we partnered with to give us access to their material testing samples. So they have a database of just thousands of materials. All they do is basically test materials and publish their results. And if you have SolidWorks Simulation in 2014, you have access to that. So we choose Apply, Close. Notice now we have a check mark next to our parts telling us, oh, step one's done. So let's move on. Step two, connections. How do these components interact with one another? Well, we have three options: bonded, allow penetration, and no penetration. So bonded basically is saying these things are perfectly connected to one another, whether it's glued, welded, doesn't matter. They're stuck together and they're not going anywhere. Then you have allow penetration. And allow penetration is interesting because, well, it's not real. It's basically saying if I were to push on this table, I'd push right through it. So we have no interaction. If I hit something, well, I'm going to go right through it, kind of like a ghost or something like that. And then no penetration, well, that's kind of like letting SolidWorks figure out the actual physics behind it, what's going on. Like if I throw a ball at the wall, it's not going to go through it, right? It's going to hit it and stop. That's kind of what no penetration is. Things can touch, but they can't go through it, but they're also allowed to separate. So we're going to go with bonded here and just pretend that everything is basically connected to one another. Then we're on to step three, our fixtures. Now there's a whole lot of different fixture types. We have these three basic ones, kind of saying how it's clamped or how it's held in place and giving you a nice little animation. You can even come in here and go into more advanced ones if you wanted to. Say I wanted to, this one's interesting, use reference geometry. If I want to see what happens when something gets pulled an inch, I can click on a face and literally move it an inch and see what happens. And you can use reference geometry to do that. We call that prescribed displacement. So you can have that if you wanted to. I'm just going to say this is fixed here, and that's the only place I'm going to hold it. Pretend that everything else is something that we're interested in. So step four, let's go on to our external loads. So I know that when this thing lands, it's going to have basically the weight of the plane on it. So I'm going to come in here and click on this face as well as that face and apply 6,000 pounds to it. Now I have two options, normal and selected direction. Basically, I can click on that face and it's going to be the loading applied normal to whatever face I clicked on. Or the other option is selected direction, where I can choose some sort of reference and apply the force along that edge or in reference to this face. So here, if I were to come in here and say, I want to go with this edge, now all of a sudden I apply my loading. And you see the way the arrows are going now? Now the arrows are lined up in that direction with that reference geometry. So that's not the right direction, so I can click reverse direction. Now one thing that is interesting though is I clicked on two faces and I keyed in the value of 6,000. If I were to run this, it's probably going to fail because I just applied twice the loading to it. And that's here. This is very important, this per item versus total. So depending on every entity you click, it'll get distributed, or it can be per item you clicked. So we can do that. And one other thing I wanted to show you guys that comes up quite often that a lot of people didn't know is this here in pressure, or even force as well. There's this checkbox here for non-uniform distribution, where you can define a coordinate system and then you can describe this loading with these coefficients and this shape curve down here. So just want to point out that that's available to you guys if you need to apply something like a hydrostatic pressure or some sort of non-uniform pressure or loading. You can do that there. Next we have our mesh. Now meshing, to me, in SolidWorks, using this auto mesher is probably my favorite feature of this tool. It can look like this, something very, very simple with this slider right there with it set to the center. And we can go to the left or to the right, sliding it, making it more coarse or more fine. And what we're doing there is we're defining the size of our mesh elements or the size of the measurements we're going to take. Now, you can leave this in the center because it's unique to every single model that you have. There's a function behind the scenes that predicts an appropriate size based on things like the volume and the surface area. I'll just be honest with you guys, I don't know the equation behind the scene. That's something that I have kind of guarded secret. They don't want me to start my own company. Anyway. So I can leave that in the center, and I can click the check mark, and that's all I need to do, right? Auto mesh. Or I could do this in a different way. If I wanted to mesh it in a different way, I could come in here and click Mesh Parameters, and I can change between the meshing algorithm, curvature-based or standard-based, or standard mesh. I can even go down to the advanced, and I can choose things like my Jacobian points, how many different measurements I'm going to take to understand the quality of my mesh, whether things are distorted or not. I can even come in here and say, you know what, I want to make sure I use linear edges rather than parabolic edges. So you can come in here and you can really get into the weeds of the meshing process, or you can take the prediction for the auto mesher and take the default. Draft quality. Guys have any questions about the mesher? Any of these settings in here? Okay. Now what? Well, we run it. So what have we done so far? It started with CAD, then it moves into our analysis setup. This is step 2, setting up the problem, breaking it up into those smaller pieces. And then we have to run the analysis. Now we hand it over to our teammate, the computer, to solve these problems at every single point that we just took. And it's going to stitch it all back together and put it all together for us in this nice, pretty picture. So behind the scenes, if I come in here, I right-click and I say details of my mesh, we can tell you that it actually solved so many equations, about 60,000. Where's the degrees of freedom? 60,000. Whatever. It solved about 60,000 equations there for us behind the scenes, just like that. I can't even solve 2 plus 2 that quickly. That's a lie. I can do that. All right, so here's our stress. So remember, stress is actually the third thing that we're solving for. So if you want a very, very, very accurate answer, you want to look at the displacement. So there are instances where if you keep refining the mesh and you're taking measurements of the stress, you'll find that your answer is never converging. It's never leveling off. Does anyone know why that might be? Ever hear of stress concentrations? It could be what we call a singularity point. So stress, we'll just talk about this, is basically force over the area. If you keep taking smaller and smaller measurements, you're changing the size of the area, making it smaller and smaller and smaller and smaller. And as the area approaches 0 or gets smaller, your answer just keeps getting larger and basically goes to infinity. So that can happen where you don't have a converged answer for stress, but displacement is something we're actually measuring. So you can have convergence of your displacement without convergence of your stress. So I just wanted to point that out. That'll happen at something like singularity point or like a corner where you don't have a fillet on. Try to avoid stress concentrations if at all possible, but I'm sure you guys know that. Where? Here? Yeah.
Can we refine the mesh at certain area?
Hmm?
Can we refine the mesh at certain area?
Of course. Mm-hmm. Yep, we'll get into that. I'll have to look at that because there's a lot we can do with that. So all right, so here's the deal. Basically, I'm kind of done with the presentation. So for the next 35 minutes, I'm just going to like poke around with the software up here, just so you guys are aware of that. So if you guys do have any questions or want to see anything, that's fine with me. So you wanted to talk about why that was.
When you in the options for accuracy, which Jacobians are obvious, when you get results, what do you look for? Do you look at ratios, look at percentage? How do you know? That's a lot of work.
So the first thing, the reason why I think these results look this way, where they're not perfectly symmetric, is because it's not a symmetric model. Even though it looks symmetric to us, when we break it up into those triangles, the mesh elements, it's actually not symmetric. So that's the first thing I would look at. You asked about the details. You want to define the accuracy of your mesh and look at it. You're going to want to look at this number right here, the aspect ratio. That's how we define the shape of the element. So that's defining whether they look like good elements. So the aspect ratio is the